we are going to cover our third chapter, Conditional Probability and Independence. Now, this chapter is a nice passage to the next part of this class where we are going to study random variables, the concept of conditional probability and the concept of independence. They are too important for the sake of completeness of this course. So please spend enough time to understand the concepts here mentioned in this chapter. So here's the outline for this chapter. We are going to define the concept of conditional probability, and we are going to use conditional probabilities or conditioning to calculate probabilities. Then we are going to go through the independence of events. We are going to describe how events can be independent. And then one of the most important theorem of the probability theory will be mentioned, which is called the Bayes theorem. Now, it is not very easy to understand how Bayes theorem helps in calculation of formulas. The best way to learn Bayes theorem is to solve enough questions related to Bayes formula. So let's start with conditional probability. So what does that mean, the conditional probability concept? So conditional probability is the probability of an event when some partial information about the experiment is available. So let's just say you have performed the experiment. You have not observed the actual outcome yet, but you have some partial information about it. So for example, some of the outcomes are not possible anymore. Only the remaining outcomes are. So in that case, the probability measure for a certain event may change. For example, consider the probability that it will rain tomorrow. So when you are watching this video, imagine a probability about raining tomorrow. Now consider the probability that it will rain tomorrow given that it has rained today. Now based on the information on today, so you have observed that it has rained today, what would you think about the probability of raining tomorrow? Now, I have given you some partial information about today's weather. So you have observed today, and based on this observation, I would like you to recalculate your probability about tomorrow. Now, you see, observing rain today will change the anticipation on tomorrow's weather, right? Now, you do not see the weather today, and if I ask you what is the probability that it will rain tomorrow, you will say something. But if you observe the weather is rainy today, then you will think it is also possible to have rain tomorrow as well. So your anticipation about the probability of rain tomorrow will conditionally change on that observation. So basically, the conditional probability is the probability of an event when we have some information about the experiment. Now, even we do not have any partial information available about the experiment, again, we can use the concept of conditional probability to compute some events' probabilities in a more easier way, and we are going to practice all of them in this chapter. Now, let's try to understand conditional probability again over a simple random experiment. And the classical random experiment that we are always giving as an example is the toss of two fair dice. Now we know that this random experiment has a sample space with 36 possible outcomes. And all of these outcomes are equally likely to occur, and the probability of each outcome is 1/36. So please remind yourselves with the sample space of this random experiment. Okay, so the question here is this. It's a simple probability question which you can easily solve by your knowledge on the previous chapters. What is the probability that the sum of the upturned faces equals to 8? So because our random experiment has a sample space with equally likely outcomes, which means each outcome has the same probability of 1/36, we can calculate the probability of this event by first counting the number of outcomes that correspond to this event. So for which outcomes we can say the upturned faces equals to, the sum of the upturned faces equals to 8. We can say for 2, 6, 3, 5, 4, 4, 5, 3, or 6, 2, we can say the sum is equal to 8. since this subset of the sample space represents this event and it has 5 elements, we can simply say that the probability of this event is 5 over 36 since we have a sample space with equally likely outcomes. It is just that easy to solve this probability question, right? Now, we are going to re-ask this question, but this time we are going to give a partial information about the experiment. Suppose we toss 2 fair dice, and an observer has seen the result, but does not give the full information, full outcome. The observer tells us only that the first die shows a 3. Now, we have performed this experiment. We do not have the actual outcome, but the observer tells us only the first die shows a 3. Now the question is re-asking, what is the probability that the sum of the upturned faces equals to 8? So the question is asking the probability of the same event. This time we have a partial information where we know that the first die is a 3. Now with this partial information, unfortunately we do not have a sample space anymore which has 36 outcomes, right? So right now, our sample space reduces to this sample space. Because now that we know the first die shows a 3, the only possible outcomes we may have as a result of this experiment is 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. So the question is asking the probability of the sum of the upturned faces equals to 8. Now, in this current sample space, which outcome or which outcomes or outcomes correspond to the event of the sum of being equal to 8? There is only a single outcome, which is 3, 5. So our event of interest now becomes a single element event, which is 3, 5 only. There is only one outcome in that event. And my sample space now has 6 equally likely outcomes. Now, given that the observer tells us the first die shows a 3, because our sample space reduces to 6 equally likely elements, and our event reduces to a single element subset, now the conditional probability of this event would be 1 over 6. Now you see, when we have partial information on the random experiment, our sample space may change and the event of interest may change. So how did we solve this question? Basically, we need to give a general formulation to what we have done in the previous example. So we are going to generate a general formula which can calculate the conditional probability of events. So it says if we observe that event F has already occurred, the probability of event is denoted as P of E in F. First of all, let us represent the conditional probability concept mathematically. So remember, probability is the ordinary probability function, and we have E given F here. E is the event of interest. We are asking the probability of E. However, after this vertical line, we have a partial information about the random experiment. So our random experiment says that event F has been observed, event F has occurred. So what is the conditional probability of event E given that we have observed event F has already occurred? So this representation gives us the conditional probability, the probability of event E on the observation of event F. Please do not think that this is asking the probability of event F. The question is not asking the probability of event F, it is asking the probability of event E, and it is giving you information on the fact that event F has already occurred. Okay? Now, how can we formulate that conditional probability? We have this very simple and easily understood formula. If you are interested in the probability of event E, given that event F has already occurred, you can calculate that conditional probability by calculating the probability of the intersection of these events, assuming that nothing has occurred yet, divided by the probability of the observed event, assuming that nothing has occurred yet. Okay, so when you are calculating the right-hand side here, the formulation, you are just going to assume that nothing has occurred yet, neither E or has occurred, then you are calculating the probability of the intersection of this event and the probability of the observed event, assuming that nothing has occurred yet. And this ratio will give you the conditional probability of event E given that F has already occurred. Now, of course, if we want to have a usable formula here, the probability of the observed event F must be different than 0, otherwise this ratio would be indefinite. And actually, that wouldn't be logical, because if somebody tells you that F has already occurred, then the probability of F obviously must be positive. For an event which can occur, the probability of it must be definitely positive. So let's focus on this first question. We are going to practice the conditional probability formulation we have just seen in the previous page. It says we toss 2 dice. Suppose that somebody has told the sum is equal to 8. Now you see, we have this random experiment, but when the outcome is determined, an observer tells us that the sum is equal to 8. We do not know the actual outcome, we only know that the sum is equal to 8. So we have a partial information about the outcome. What is the probability that the upturned faces show the same value? Now we are going to solve this question using the conditional probability formula. And in order to do that, we are going to decompose our question. Now, in this question, one event has been observed and another event's probability is being asked. We need to determine these events. First of all, if you perform this experiment will have 36 equally likely outcomes, as you have known in our earlier chapters. Now, the question is asking the probability of the event that the upturned faces show the same value, right? Now, without any observation, we are just representing this event E. And if we want the event where the upturned faces show the same value to occur, we need to observe one of these 6 outcomes, right? So we are basically creating this subset without thinking about the observation, okay? So in this random experiment, if we observe the outcomes 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or 6, 6, then we say that event E has occurred, therefore event E is represented by this subset. Now, on the observation. The observation says the sum is equal to 8. Now, if we want to represent the observed event with notation F, then F is going to be the subset of the sample space containing these 5 elements, right? 2, 6, 3, 5, 4, 4, 5, 3, and 6. Now, this is the observed event in the subset form, and this is the event of interest for which the probability is being asked, again in the subset form. Now, the question asks the probability of the event that the upturned faces to show the same value, given that the sum is equal to 8. So the probability of event E, given that we observe event F. Now, this is formulated as the probability of the intersection of these 2 events divided by the probability of the observed event, assuming that we have not observed anything yet. Okay, so when you are solving the right-hand side, remember again, you are not going to assume that you have seen anything. Okay, you are just trying to find the probability of these 2 events, the intersection event and the probability of the observed event. Now, what is probability of the observed event or probability of F? It is simple, because in this random experiment with equally likely outcomes, we have 5 outcomes in this subset. Therefore, the probability of this event should be 5 over 36. And how about the probability of E intersection F? Now, the intersection of these 2 events, E intersection F, there is only a single outcome as the common element of these 2 subsets. Therefore, E intersection F consists of only single outcome, and the probability of the single outcome is 1 over 36. As a result, the conditional probability of given F is 1 over 36 divided by 5 over 36, which is 1 over 5. Now, actually, without making any calculation through this formula, once you have determined that the event F has already occurred, and F has only 5 outcomes, and in only one of them we have the corresponding event of the sum to be equal to 8, we can again have answered this question as 1/5. However, please, I'm requesting this from you, when you are solving a conditional probability question, always follow this procedure, because when you are going to see the next practice, the next question, you will realize that it is impossible to solve these questions without writing this formula. So this formula, this expansion of the conditional probability on this formula is very important to solve much more complicated questions. Now we're going to practice this in this question too. Now we are going to read the question and we are going to define the events mentioned in this question, and for these events we are going to determine the probabilities. So we first need to develop the given information of the question with mathematical notation, as you know. Then we need to identify what is being asked, and we are going to use many different propositions of probability and the conditional probability formulation to answer these questions. It says, in a university, 62% of the students own an iPhone, while 44% of the students own an LG mobile phone. Now you see, 62 plus 44 is greater than 100, which means some of the students may have more than one mobile phone, two brands of mobile phones, both an iPhone and LG mobile phone. And obviously, there is this possibility that some students may not have any of these brands. It is known that 20% of the students own neither of these mobile phones. So there are 20% of the students owning none of these brands, neither an iPhone nor an LG mobile phone. So we know this information. Now we randomly select a student. The first part of the question is asking this. We randomly select a student, and we know that the student owns an LG mobile phone. So we randomly select the student and ask the student, do you own an LG mobile phone? And he or she owns an LG mobile phone. The next question is being asked, what is the probability that the student also owns an iPhone? Now that probability is not equal to 62%, because we have randomly selected a student and we have a partial information about that student. That student owns an LG mobile phone. That 62% probability was the probability of a randomly selected student to own an iPhone if we do not know any information about that student. So we have some partial information about that student, and based on that partial information, we are asking the probability of another event. So how we are going to solve this question? So before skipping to part B and part C, let's solve part A. In order to solve part A, first we need to summarize the given information in the question in a mathematical representation. This is basically the most important part of the solution. Now, we are going to define these following events. I is the event of the randomly selected student on an iPhone. So remember, our experiment is what? Our experiment is based on selecting a student randomly. And if this student owns an iPhone, we will say that event I has occurred. If this randomly selected student owns an LG mobile phone, then we will say that event L has occurred. So we are basically representing these events as letter I and letter L. Now the question gives us this information. The probability of a randomly selected student to own an iPhone is 0.62, because we know 62% of students own an iPhone. And the probability of event L is equal to 0.44. And we also have another information. So the probability of a randomly selected student to own neither of these mobile phones was 0.20. So how do we represent the event of having neither of these phones? So it should be the complement of I union L. You know, I union L is owning at least one of these brands, and the complement of this event is the event of having none of these mobile phones, and therefore the probability of I union L complement is 0.20. So these information are given by the question itself. Now what can we extract further? Now you know, by the first proposition of probability, the probability of an event can be calculated through the probability of its complement. Now we know that probability of I union L complement is 0.20. Therefore, the probability of I union L must be equal to 0.80 as 1 minus the probability of its complement. Now, what does that mean? Probability of I union L equals to 0.80. This means if you randomly select a student, the probability that this student owns at least one of these two mobile phones is 0.80. Now, further, you know the second proposition of probability. The probability of the union of two events is always equal to the probability of the first event, the probability of the second event, minus the probability of the intersection event, right? However, in this formulation, we are using the same equation to calculate the probability of the intersection event. Therefore, as we can compute the union event's probability, we can also write the probability of the intersection event as the probability of the first event plus probability of the second event minus the probability of the union event. Okay, so the second proposition, the equation given in the second proposition of probability, can be used in different manner as we have stated. As long as if you know the three other values, you can always calculate the fourth value. Now we can calculate the intersection probability as the probability of the first event 0.62 plus probability of the second event 0.44 minus the probability of the union, which we have calculated just a minute ago. This means if we randomly select a student from this university, this student may own both of these phones with 0.26 probability. Or in other words, 26% of the students own both of these mobile phones. Now, we have summarized the given information of the question. We have also generated the probability of the union of I and L and the probability of the intersection of I and L. So we have calculated these two values as well. Now we are ready to solve the first part of the question. So let us remind again, what is the question? Given that the student owns an LG mobile phone, what is the probability that the student also owns an iPhone? So what is the given information? The given information is L. Now the probability of I being asked. Okay. So we are going to rewrite this probability as the probability of I given L, or in other words, the probability of that the student owns an iPhone given that the student owns already an LG mobile. Okay, so the question is asking this probability. And how do we expand this probability by the conditional probability formula? Assuming that we have observed nothing yet, we are writing the probability of the intersection of these two events in the numerator and the probability of the observed event in the denominator. And as you remember, we have already calculated the probability of the intersection event as 0.26 and the probability of the observed event as 0.44, and that ratio gives you a 13.20. Okay, so it is definitely different than 0.62. So when we randomly select a student and that student tells us that she owns an LG mobile phone, then the probability of that student to own also an iPhone is 13/22, which is larger than 0.5 again, but not equal to 0.62. We are going to solve the second part. In the second part, the question is telling us, given that the student does not own an iPhone. So this time, the information is given as the student does not own an iPhone. What is the probability that the student owns an LG mobile phone? Of course, at this point, we are going to forget about part A. So part A is an independent part. Part B is asking something different. So what we know about this randomly selected student, this student does not own an iPhone. What is the probability that the student owns an LG mobile phone? So you see, if the student does not own an iPhone, that student may own an LG mobile phone or may own another type of brand, okay? Because you remember there are some students which do not own any of these mobile phones. So what do? First, we need to represent this conditional probability question in a mathematical formulation. So what is being asked? What is observed? The observed event is the student not to have an iPhone. which is the complement of event I, right? So I complement has been observed. Not I, but I complement has been observed. The question is asking the probability of event L, the student to own an LG mobile phone. So the student does not own an iPhone. This is observed. And the probability of owning an LG mobile phone is being less. So how do we expand this conditional probability? Again, with the same structure. We are writing the probability of the intersection event of these two events to the numerator, and writing the probability of the observed event in the denominator, and we are assuming that nothing has been observed yet. We are basically calculating these two probabilities starting from scratch, and the probability of I complement can easily be calculated by subtracting the probability of I from 1 by the first proposition of probability, and that is 0.38. 1 minus 0.62 is 0.38. Now, for L intersection I complement, you see L intersection I complement and L intersection I. So these two intersections here, L intersection I complement and L intersection I, they are disjoint from each other, right? So these two sets, these two intersections must be disjoint from each other because they wouldn't have any common elements. And when you take the union of these two intersections, you are going to get L. Therefore, by the additivity axiom of probability, we know that the probability of event L can be decomposed as the sum of probability of L intersection I complement and L intersection I. So the sum of this intersection probability and this intersection probability must give the probability of L. Hence, we are going to calculate this probability of the intersection by subtracting the probability of L intersection I from probability of L. And we have calculated these probabilities in the previous page. The probability of L was given by the question is 0.44, and the probability of L intersection I was already generated by us through the solution using the propositions of probability, and it was 0.26. Therefore, the result is 0.18 divided by 0.38, which is 9/19. So let's go to the final part. So this time, we randomly select a student, and that student owns at least one of these mobile phones. So we ask this student, do you have an LG mobile phone or an iPhone? The student says yes. But we do not understand if the student owns both of these mobile phones or only one of these mobile phones, and we do not understand which type of mobile phone he or she has. So we only know that at least one of these mobile phones is owned by the student. This is observed. Now the question is asking, what is the probability that the student owns both mobile phones? So what is the given information? At least one of these mobile phones is owned by the student, which means L union I. L union I. Remember, union means at least one of the events to occur. The question is asking the probability of the events of owning both mobile phones, and owning both mobile phones is represented by L intersection I. So the question is basically asking the probability of L intersection I, given that L union I has been observed. So the student tells us at least one of these mobile phones is owned by me, and what is the probability that I own both of them? Now, again, we are using the conditional probability formulation. In the numerator, we write the probability of the intersection of two events, and we divide it to the probability of the observed event. And we have already computed the probability of I union L, which is the observed event, which was 0.80, if you remember. And the probability of the intersection of these two events, so let's compute the intersection first. What is the intersection of I and L and the union of I and L? Obviously, the intersection of I and L is just going to be a subset of the union of I and L. Therefore, the intersection of these two subsets is also the intersection of I and L. And that would have 0.26 probability, and 13/40 is the probability, conditional probability, that is being asked in the third part of this question. If you want to get better in conditional probability calculations, my friends, there are two recommendations for you. First of all, always use the set notation and summarize the given information of the question using the set notation and the probability function. Okay, first convert everything given in the question into notation. Then you need to harmonize what you have learned in axioms of probability, in propositions of probability, and the conditional probability expansion formulation that you have learned here. Now you see in this question we are basically using everything we have learned so far. So if you can harmonize all of your knowledge starting from the beginning of chapter 1, then you will be capable of solving such questions as well.